Okay, here we go with day one, section 12.2 for core geometry. So just before I go any further, with this being the first online lesson for our school closure plan, just make sure you guys understand that you need to contact me whenever you feel like you need any type of help or assistance, whether it's during my virtual office hours, morning or afternoon. Shoot me an email, use the Google chat room that I've opened. However you want to contact me, contact me. I'll get back to you as soon as possible. The chat room is probably the easiest. It pops up on my phone right away. Emails can kind of get lost in other emails because I get emails for personal and business or personal and school uh, throughout the day. So those can kind of get mixed up between parents and administration and students. The Google chat's just for you guys. So I'll get back to you pretty quickly. And also, one of your classmates can answer it as well if need be. I'll also post a lot of things in there for the daily agenda and for office hour links and when we do our live teaching and our live big group review sessions. So here we go with 12.2. Don't forget to go back and look at 12.1. There was a warm-up in there for you guys in the daily agenda in the day one folder. Make sure you take a look at that. Don't forget to do the exit ticket. That's also in there. You don't have to do the exit ticket right now. You can wait until you get some questions answered after you do homework. Don't forget about the homework. And we will take this one day at a time. Okay, here we go. So remember, we did skip to Unit 12 because we wanted to do Pi Day, but we did not end up getting to do Pi Day. So we're going to stick with Unit 12. I'm not going to cancel out 12.1, so we're just going to keep moving along here. So today we're going to focus on chords. Okay, so a chord is a segment whose endpoints are on a circle. So if I draw us a circle real quick, there you go. So a chord, that's a chord, that's a chord, that's a chord. So a segment whose endpoints are on a circle. So we would say that CD is a chord. So you can already start picturing that as being something like in a given statement in a proof. So we're going to go through a couple theorems here, theorem 12.4, 12.5, 12.6, and their converses. So they're kind of just bundled together. So we're just going to read them as they are. Make sure you guys see where I am reading. So within a circle or in a congruent or incongruent circle, so these could be two separate circles, but they're of the same size, same radius, same diameter. Congruent central angles have congruent arcs. So congruent central angles have congruent arcs. So since we did skip ahead a little bit, that word central angles, so that's a central angle. Right? It comes from the center of the circle and its sides of the angles extend out and they are both, they are radii. Okay, so they are congruent. You can already picture if I was to draw a chord right like that, we have an isosceles triangle. Okay, so that will pop up. So what this is saying is if you have congruent central angles, then you're going to have congruent arcs. So if these are congruent, they're not vertical angles. Okay, they're not vertical angles. They don't share opposite rays. Then these arcs are going to be the same. So that arc and that arc. And that just kind of makes sense. If you're opening up these central angles, it's going to determine how much of an arc that you have. So if I come over here and say that this is the same as up here, then this arc is going to span the same amount of distance. And then the converse is true. If you have congruent arcs, then you have congruent central angles. Okay? So that goes back and forth. Let me erase that just so we can free up what this is saying down here. So if angle AOB, which is right here, is congruent to angle COD, which is right here, then notice how this is written. Arc AB is congruent to arc CD, and vice versa. So converse, if arc AB is congruent to arc CD, then the central angles are congruent. Okay, when we go through these, start picturing what the algebra problems are going to look like. Start picturing what the proofs are going to look like. Okay, start making those connections. We know that's kind of what it's all building up to. Theorem 12.5. Within a circle or incongruent circles, congruent central angles have congruent chords. Sorry. So within a circle or congruent circles, congruent central angles have congruent chords. Okay? Maybe I jumped ahead a little bit for you guys, but I just knew what you guys would be thinking as we looked at that top one. So if AOB and angle COD are congruent, then AB is congruent to CD. Okay, we already know that these are congruent. Okay, they are all radii. So now we're saying that these chords that are the base of those isosceles triangles, they're going to be congruent. So one more time, if angle AOB is congruent to angle COD, then the chords AB and CD are congruent. And the converse to that is if you have congruent chords, then from their endpoints, the central angles are congruent. From their endpoints, the central angles are congruent. 12.6. Within a circle, congruent chords have congruent arcs. So we have this chord with this arc. It's going to be the same thing. If these chords are the same, I mean, it's cutting off the same portion of the circle. And the converse is true as well. Arc AB is congruent to arc CD. So if the arcs are congruent, then the chords are congruent. All right, practice number 1. In the diagram, circle O is congruent to circle P. That means they have the same radius. given that BC is congruent to DF, so right now we know these are going to be the same. And now we know that BC is congruent to DF. What can we conclude? Well, we know that angle BOC is congruent to angle DPF and then we have arc BC is congruent to arc DF. Okay. Up here, this is theorem converse of theorem 12.5. Down here, it's theorem 12.6. Okay, just zoom out there, let you guys take a look at that. And then we have another theorem, theorem 12.7. It says within a circle or congruent circles, so that within or congruent circles, that's just like we had above. Okay, we had two congruent circles. So that's why they keep saying that. Chords that are equidistant, there's another fun word, from the center or centers are congruent. So chords equidistant from the center or center are congruent. So if you have a chord that's the same distance away from that center, keep in mind, as you start moving through the circle, okay, that chord's going to get smaller and smaller and smaller. But as you get closer to the center, it gets bigger. Then once you pass the center, it's going to get smaller and smaller and smaller again. So if you're the same distance away from that center, okay, it's going to be congruent. These right angles here are just telling us that that's the true distance, okay? You're not going to measure over there to that chord. You're not going to measure way down here to that chord. You want to measure down to a 90-degree angle. That tells us that we're measuring basically the shortest path. Converse, within a circle or in congruent circles, congruent chords, basically they're the same distance from the center. Congruent chords are the same distance from the center. So what is the length of RS in circle O? What is the length of RS in circle O? So what we know is since we have OQ and this segment over here, which we actually don't have a letter for, since they are the same distance away, we know that the chords are going to be congruent. So we know that PR is congruent to RS. Because they're the same distance away. We know that PR equals PQ plus QR. We know QR is congruent to PQ. Sorry, PQ is congruent to QR. So basically, these are the same thing. So we can say that PR equals 12.5 plus 12.5, which is 25. So RS equals 25. Looking at the next one, what is the value of X? Pause it right here, see if you can do that by yourself. But what we should be looking at is, since this chord is 36 and this chord is 36, it means that they are both the same distance away from the center. So that means that X equals 16. Okay, top one I kind of went more step by step, wrote it out. Wasn't a proof, but just kind of walked that one out for you guys. Doesn't say justify or show your work, or not show your work, but it doesn't say justify or explain. That one's easy enough just to look at. All right, theorem 12.8. In a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. So if a diameter, so AB, is perpendicular to a chord, so it's perpendicular to CD, then it bisects it. Okay. Because that diameter cannot be up here. It's not a diameter then. Remember, a diameter has to pass through the center. If it was shifted off the center, then it would just be a chord. And if it came through at a different angle, then it wouldn't be perpendicular. So the idea that it goes right through it at a 90-degree angle makes it split that chord CD into two congruent halves. Notice we have the two hash marks, and then we also have the hash marks on the arc saying that arc CA and AD are congruent. Theorem 12.9. In a circle, if a diameter bisects a chord that is not a diameter, then it is perpendicular to the chord. So if a diameter bisects a chord that is not another diameter, then it is perpendicular to the chord. Okay. Sort of saying the same thing above, but it's kind of just focusing on that perpendicular right angle. I guess you might want to argue, if you wanted, that maybe that one should be established first. And theorem 1210, in a circle, the perpendicular bisector of a chord contains the center of the circle. So the perpendicular bisector of a chord contains the circle, because that perpendicular bisector, again, it is a diameter. And since it's a diameter, it has to pass through the circle. All right, what is the value of r to the nearest tenth? All right, so we know that this is going to come down here, and it's a right angle. Now, this could easily extend all the way up and all the way down. This could easily be a diameter. Okay, it's the idea that it's coming from the center to this chord and making a right angle that tells us that it bisects this chord LM. So LN and NM are congruent. Okay, so that's theorem 12.8. So LN equals 1/2 of 14, which equals 7. And we have a distance away from the center, which is 3. And notice that we've created a right triangle. Anytime we're missing a side of a right triangle, we're using the Pythagorean theorem. So a squared plus b squared equals c squared. I'm going to substitute in what they give me. So 7 squared plus 3 squared equals r squared. So this is 49 plus 9 equals r squared. So 58 equals r squared. They told me to round it to the nearest tenth. So r equals, we got to take the square root of that r squared to cancel out that r squared. We're left with r equals the square root of 58. So r is about 7.6. All right, we're going to turn the page. We got one more problem. Go ahead and pause it here. Try it yourself. You're looking for y to the nearest tenth. Nearest tenth. Start thinking about that. They're already thinking, they're telling you to think that you're going to be rounding. Maybe you want to be thinking about taking the square root of something. Maybe that's something that tells you Pythagorean theorem. So what we can see here is this chord AF is bisected by CB. So CB bisects AF. So that tells us that CB is perpendicular to AF. So there comes our right triangle. So if we're looking for the side of a right triangle, we need to have two of the three sides. So what is that side? Well, they're giving us this radius here of 15. All radii are congruent, so this is also 15. So here comes our Pythagorean theorem. Remember, 15 is across from that right angle. So out of A, B, and C, it is C. So this is going to be y squared plus 11 squared equals 15 squared. So that's y squared plus 121, which equals 225. Y squared equals 104. To cancel out that squared, we're going to take the square root. So y equals the square root of 104, which is about 10.2. All right, like all the sections, make sure you're getting used to the types of problems that are going to be asked, the things that keep reoccurring, the things that keep popping up. Your homework is there at the bottom. Make sure you're taking a look at that. For homework quizzes, for unit quizzes, unit tests that'll be popping up, make sure you're keeping an eye on the Schoology calendar. Make sure you're emailing me, Google Chat Room, and the virtual office hours whenever you guys are ready to ask questions. And yes, we will be doing a live review session here in the near future. Okay, so keep an eye out for that announcement. I'll make sure everyone gets emailed, and that announcement and date shows up everywhere. Schoology calendar, email, Google Chat Room, in the daily agenda. So keep an eye out for that.